Hello, everybody. My name is Kevin Kochnik. I'm the founder and CEO of Chemical Q Device. This is Wednesday, August 28th, 2024, for the 148th session here. This is large multimodal models for spectrometric determination of an organic compound. So if you've ever, gone through, chemistry degree or biochemistry, whatever, you probably had to, if you're in grad school, have taken a course in spectroscopy. So spectroscopy is the study of light. So we're talking about proton NMR, C13 NMR, depth NMR, IR spectroscopy, mass spectrums, those types of things. And I really want to focus on this one because the previous manuscript, I was able to prove that, I could take image clips of, reactions and it would suggest new ones like the AI software would, or even a spectrum, and actually 3.5 Sonnet, it's a Claude model, did quite well with that last week, and it would and then analyze these spectra, or even something just deep inside the text, and that also with text as well. So this specific study really focuses in on images. So in specific spectral images. So spectrum you obtain when you run a proton NMR experiment or C13 or IR spectroscopy. It's very fast. And the reason why I did this is because what's on the market right now, what's shown is you're looking at least 6 steps, to solve a lot of these unknown problems where you have to pick the peaks and these types of things. In the large multimodal workflows, the only thing I had to do, because one of the models, the Google model, Gemini, only accepts one image to upload, is for all of them, I included high resolution images into a single image. And then the prompt is basically saying, please return to me back the organic unknown. It's 2 steps: upload high resolution images and then return back to me the organic structure. Okay, so what we see, and actually you can take a look at the manuscript. This Chem Archive, along with the previous Chem Archive, are both up. And I go in depth as far as the academic studies. I'm not going to mention here, but this is basically kind of like the state of the industry stuff as far as the software that's available. Now, when we're talking about with these types of vision or computer vision models, we're typically talking in the millions of parameters. But when we're talking about large multimodal models, we're talking hundreds of billions of parameters. And if not, the chat GPTs, typically they state that they're over a trillion parameters. So they're just more substantial models as opposed to what you're going to see, on the market today. And a lot of the academic research I still see is kind of, I compared to this, I don't really think it's going to hold up too much longer. Now, here's the 3 prompts. Now, the first one, 3 of the models were able to get the right answer. It was quinoline, or it's benzopyridine, is another way of saying that. And the models that I used were GPT-5, organic chemistry, ChatGPT 4o. The 3.5 Sonnet was able to get an isomer. I checked for isomers. I think there's 35 commercially available isomers of quinoline. So meaning that it has to get one of those, it has to separate that molecular formula that I provided for the other 34 isomers. And then ChatGPT 4o, which is on the market here, and also there's Google Gemini Pro 1.5, and it just did not perform well on pretty much any of the tasks. So, like I said, 3 of the models were able to get this answer for the quinoline, whereas 2 other ones, like I said, the 3.5 Sonnet only got an isomer, and then the Google Gemini was just way off. And then here's the answer for, and I'll show you a structure for prompt B and prompt C coming up here too. And I chose 2 different prompt templates, either provide this 2-sentence one or the shorter one, interpret information 1 step at a time, create a molecule name at the end based on your findings. And they didn't seem to matter, right? So they both went through spectra sequentially, typically. So they go, if I put a proton NMR, the first in this big high resolution image, it would talk about the proton NMR and the characteristics of it, and then it go through if it's like a IR C13, typically sequentially. So it did that very well as far as following some type of organized framework and based on a big, large, high resolution image. Okay, so here's the one so this is basically LMM scoring. So there are no benchmarks out for this. And there's a lot of large language model benchmarks because it's been around for a while. It's at a very high level. If you ever try to just try to find, very specific details hidden amongst, and I've proven this, like, 4 or 5 different documents, it can search through and find in a specific document as you need. Now, in large multimodal models, they're getting better. So we're talking, in this study, it's just images, but it could include videos or speech or audio or these types of other modes. That's where it gets the name multimodal. Okay. So I labeled these C1 for condition 1 and all the way up to C5 for condition 5. So condition 1, does it provide the correct generation context? The first 4 typically did, except for the Google Gemini model. And then number 2, models generation order similar to Spectra. Most of these, I think all of these that I tested on these 3 prompts, they did. And then condition 3, some chemical information properly interpreted, meaning that it gets the gist of it, like it gets the spectra, gets these types of things, but it's just making too many errors to make a correct, structure. And even sometimes condition 4, most chemical information properly interpreted. If it gets to that point, then it has a shot at doing the correct chemical ID of the unknown. Now, the scale in the paper, in the manuscript, I just caught this, is that it is out of 5. So for instance, and this is prompt 1, C1, C2, C3, you just add it up. It's simpler to get to the score, whatever. Okay, so here's the prompt A. So this is the first one. Now, what's included here, this is from webspectra.chem.ucla.edu. It's listed as an advanced problem, compound number 16. And, so with these, so for proton NMR, you always want to see, obviously there's 4 different, things that it tells as far as chemical environment, the integrations, the splitting pattern, and just, the number of different types. So if we go left to right or downfield to upfield, we see this one at about 8.75 that integrates to 1. We see another one at integrating to 1, and then another one at 1, and another one at 2, and then another at 1. And another one at 1. So if we add these up, 1, 2, 3, 4, 5, 6, 7. So that's where the 7 protons come from. Now the carbon skeleton here, and actually this, based on what you're seeing right now on this recorded version of this, the high-res image, you can see some of the splitting types, or the, basically the multiplicity of it all. Now, if we look at the C13, we can quickly spot the chloroform here at about 77. So then we start counting. So 1, 2, 3, 4, 5, 6, 7, 8. And there may have been some overlap with this. That was the only thing that wasn't clear to me. But based on all this information, 3 of them were able to get the structure. So this top one in the depth is basically the full spectrum, and then the 45. The one that counts is this 90. It's basically saying if all of these are up, it's going to be CHs. So we're going to have 1, 2, 3, 4, 5, 6, 7 CH groups. So that's coming from there. And then the other 2, this one and this one, which have 4 bonds, it's technically they each have, well, this one has 3 carbon bonds and one of them's double bonded. They're just, they're not quaternary, but, basically, if you look at that 0 spectrum, this is what's coming off, or easier seen on the C13. These 2 peaks right here are coming from these 2 carbons that don't have hydrogens or CH2s or CH3s. Okay, so going through that process, it looks good. And in fact, like if you click another button, and it'll say like, okay, here's the answer for it. And so we see as far as how well they did. So I gave the ChatGPT 4.0 its explanation. I'd say just some of it. There was, some of it that was kind of like, I think it said like, like a possible aldehyde, maybe it was just throwing it out there, but there's no oxygen here that an aldehyde would have. Now with the GPT-5 and the organic chemistry, especially with the GPT-5, and again, this is a preview model, it tended to have these chemical shifts like labeled very precisely. Like the chemical shifts of the proton spectrum are from here to here, like approximately like 6.8 to like 8.7, something like that. And then likewise, it did it for the carbon too. And the ChatGPT 4.0 and the organic chemistry, maybe more detailed than the GPT-5, but getting into some of the troubles of the exact chemical shift values were a little bit harder for it to do. Okay. So the ChatGPT 4.0 did get the correct structure. It was able to get the context right, the order, the spectra right, and some of the information. I would say the GPT-5 only had just minor things. Like when it did get this correct structure, it says something like this has it messed up the number of hydrogens it thought were on the structure. So the organic chemistry, like I said, that was the number 2 beyond the GPT-5, and it got most of the information correct. 3.5 sonnet, like I said before, it predicted isoquinoline, which is one of the isomers. And I said, based on this molecular formula, which I provide, with the spectra, it's just one of the other ones, but it just moves that nitrogen to a different position, which isn't correct. Now, the Gemini 1.5 Pro, I didn't get the sense that it was understanding the context too well. And again, the only thing it pretty much did is it just did things in order. So if it said, proton NMR, these are my findings. C13 NMR, these are my findings. Depth, these are my findings. It did that well. But I didn't really get that sense that some or most, and especially it didn't get the right structure. And a lot of the structures it returned were just far off from the other 4. And I think at one point, like a very simple ethylamine or something like that, that it provided in one of these answers. So it got a score out of 1. So again, with the GPT-5, organic chemistry, and the ChatGPT 4.0, these were the top ones for that. Okay, so the next one is the C7H11N3S. So this comes straight out of a supplementary section. This is a journal of organic chemistry within the past couple of weeks, I think this month. And I found this in the supplementary, and this is what's considered like more like real world research. The other 2 that I focused on are more just practice problems. They're typically not going to have impurities and those types of things. So with this one, I think that's where it kind of got messed up. I don't think they got their footing with this question, because if we look at the structure here, it has this diamino, and that's probably this peak at 4.9. If it's not that, then it's this one at 3 point something. But the authors didn't label it, and it wasn't integrated. So that was a tricky part. And there was just other impurities too. So like I said, these 2 tall peaks weren't labeled. One of those likely corresponds to the 4 hydrogens off the nitrogen. And there's this other, sharp peak further upfield, and then there's just other impurities too. So I wasn't quite sure. I couldn't really pinpoint it, but that definitely did not help, these models. And actually in 4 of these, they were able to, get the context of what was going on with the proton NMR, C13 and depth 135. And they could only do some of it correctly, so they couldn't do all of it. So again, it's more of a real world example here. Now, if I count these carbons here, 1, 2, 3, 4, 5, 6, I'm 1 short, and because it's a C7H11, and I think that there's overlap in the CH2s. Now, the ones that seems closest to me are probably these 2. Because this is closest to amino, and then this is close to that nitrogen as well. So there could be some overlap. But anyways, there's supposed to be 3 CH2 groups, and then we see those 2. So potentially overlapping on one of those. And like these chemical environments aren't too drastically different. But this one, should be because of the sulfur right there. And, as far as getting a close answer, I wouldn't say that was the case. Although some of them, and it's in the manuscript too, as far as, taking this further in depth. The consistent thing with the 3 prompts that I detailed in the manuscript is that the models typically go through step by step. All of them do. And like I said, except for the Gemini model, like the 4 other ones would typically give good chemical information, insight, carbonyl, carbon off of the IR, the CO double bond stretch, those types of things, it would do pretty well. So again, with this one, and also we're seeing this CH off the depth 135 right here, which would be that. So it's a little bit tricky, as far as to get the structure, and the impurities definitely didn't help. But I wanted to include something, and especially with these models are typically trained off training data, and that's what sets most of it. Like you can do fine tuning, or there could be like some additional things that you wanted to look at, additional data sets after that, like just in real time. But the feeling that I got with these are basically that, especially with this one and the next one too, is that in this one, it came out way after its training. So even though that the structure is labeled to that, it'd be really hard for it to tell, to just give a correct answer, which it didn't in this case. Now, for the previous example too, the only thing with the first one is it did come out a little bit, a lot before, like around 2000. But I also gave it two other questions that were easier, and it didn't get the correct solution. It was able to get it for that specific one. So I don't think that it's quite memorizing answers, or saying, like in this specific case, pulling information like that, this structure and this in real time, because there's not enough to support that based on the correct results, that they didn't get. And then also on the third one, that's an exam question, and I'll get to that next. And I had to solve that by hand because there was no answer online. Okay. So I just get that general sense with this, and all of these generations, all of the answers for 10 prompts are in supplementary with the Chem Archive currently, where it's at right now with the manuscript. And, basically, that's the sense I get. No matter if I go from the Web Spectra from UCLA to this one, Journal of Organic Chemistry, to the next professor's midterm exam, is that they're all kind of treated similarly, try to do it in order, and those types of things. Like we call this generalizability in machine learning, basically. Okay, so this is the last, and it didn't take me too long to solve this one. Now, the thing that pops up with this is that it has symmetry, and from the M over Z, this 202, that's what the molecular weight is of this dibutyl oxalate. And there's definitely some fragments of there, that would make sense to get this structure. I think it was the -29 and the 45. So anything in the mass spec didn't seem to rule this out. And the more conclusive things that I found are coming up. But with this carbonyl peak at 1735, that's more diagnostic of an ester peak. And then that's coming off of the CO double bond stretches there. Now, for the proton NMR, and again, this is more of a, exam problem, less on the real life data with the noise, with the impurities from the last sets of data, is that, basically it has this proton NMR. Now, the tricky thing about this one is that I kind of picked off from the proton NMR. So instead of being 2 to 2 to 2 to 3, with these CH2s and the CH3, it was coming up as 4 to 4 to 4 to 6. And I remember something like that for grad school. I was like, this has to have symmetry in it. Okay. So I haven't checked with the professor, but I'm pretty sure this is the answer. So that's what kind of set that off. Now, if you look at this peak here that looks like a quartet, I actually was not sure about that, because it integrates to 4, and I was almost 100% sure that this was a structure. Now, if I took this particular clip and then I gave it just that spectrum to GPT-5 with nothing else about atoms or anything, just the thing, and it immediately saw that this is not a quartet. This is a doublet of doublets coming off of the next CH2 down, away from the oxygen. And, the professor actually says, calculate your J values too. So that was tricky about this, beyond just the symmetry. And, just unless, and I knew I didn't have any chloros or dibromos or anything, because the molecular weight didn't have those splitting diagnostic peaks coming off of those types of atoms. Okay. But when I gave this single spectrum, I had most of this solved to GPT-5. It says this is a proton, or these are, whatever this integrating to. These are likely coming from, the first thing it says, coming from if it's right next to a highly electronegative atom like oxygen, it's actually coming from, the further 2 protons further away than itself as a doublet of doublets. And I was like, and I remember that I took 2 courses in spectroscopy in graduate schools, and I remember that from one of my professors would say, this is a unique case. If it's that close to electronegative group, you get that splitting pattern. Now, the other splitting patterns and their chemical shifts make sense as far as like this one was just taken care of that I was talking about, CH2. And then you have the CH2, CH2, CH3, which are more typical. And again, they all integrate to 4 to 4 to 4 to 6. And like I said, I've seen something like that. So, in my previous journeys there. So, the depth spectra, we see here the three CH2s. Okay. I think this is the 135 depth, CH2, 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 and then the CH3 being up. So the 3 CH2s being down, and then the last methyl being up. Okay. So, like I said, it's not the easiest problem, but I would say it's definitely harder than the other two. The 2 main things, if you can't get the symmetry. Now, what helped to rule it out for me is like a lot of times if it's like a chloro or bromo or di whatever, is you'll see those fragmentations in the mass spec. So I knew it wasn't that. And like I said, like I did probably the hardest thing that you could do with spectra right now, given these. And they're unmodified, they're state-of-the-art large multimodal models. Okay. And if you look at some of this other stuff, it's even if I just give it a single peek like that, Chat GPT or GPT-5, this preview version, which is not around anymore, it just told immediately that's not a quartet, that's a doublet of doublets, and you're probably right next to an oxygen. And that was the exact case that I was in. So even as a research tool, like if you have like 20 or 30 pieces of information, and that's overloading the LMM at this point, either context window or through data fusion, just try doing little steps too, because you can use those as tools. And it's going to be a lot more focused and spend more of its context window really on that one specific thing, as opposed to, other things as well. So the scores, nobody got a 5 on this because it didn't give detailed responses enough to qualify it that it knew it was going on. But some of them did give some, so I gave ChatGPT 4.0, GPT-5, and then 3.5 Sonnet, some information that it was getting. And like I said, all of them, pretty much if I put it in this order, this is the order in the paper. In the manuscript, it shows up as a long strip. It'll start off as EI mass spec to IR to proton NMR. And again, the thing that's unique is it's like, this is what's going on. This is what's going on. Now, sometimes it gets to the end and then it'll throw in some more information. It'll say, actually, now due to this other information, I'm seeing this. So you see this advanced problem solving that we didn't have, definitely, 5 or 10 years ago. And actually, a lot of this didn't start until May of this year with the release of ChatGPT 4.0. And like I said, it used to be you could only upload like 5 images at a time. Same thing with 3.5 Sonnet. But after I publish, it looks like you can do, actually, no, you can do 10. So for ChatGPT 4.0 or for organic chemistry or these GPT models, upload 10 documents. Now, because of the Gemini, I could only fit 1. I could only upload 1, and I wanted all of them to do it. So then I took a single high resolution image and, kept, the fidelity. And then that was what was submitted to, with the prompt. And then, so here's generation and speed. Now, the thing that sticks out, so these 3 are going to be very similar. They're trained on, similar, GPT style model, primarily, GPT 4.0 for the first 2, and then organic chemistry is 4 or 4.0. And we see here, start and stop times are very similar. Now, the words is what I'm talking about. I don't think that we're getting the full 8192 off the context window. What that means is if you subtract my prompt minus the image and all the data in it, the leftover, I should be getting more and more on my output on the words. Okay. So even though that this is a great service, I think that that's the room for improvement right now. It's typically, the Chat GPT is kind of like for the lighter weight stuff. And if you use GPT as an API call, then that's going to be your heavier weight stuff. But I can't get that to work nearly as well with the image uploads and the fusion. And I don't know if there is a direct solution to get it to work just like, Chat GPT, because there's some working parts in there. And 3.5 Sonnet, it was definitely the fastest to start. Now, due to shorter responses, about 300 words, its stop time was shorter. So it'd probably still be it's going to be shorter than pretty much these other ones if it were to go. But the main thing that kind of popped out to me is like it started faster, once I gave it this high resolution image up to about like three megabytes or less, something like that. And then the Gemini 1.5 Pro, it just feels like earlier software. I don't think it's really gone through the scientific rigor, with R&D. And on typical, like it'll do this thing and it'll pop up another kind of multicolored box. And I didn't really get started to get a text back until about 9 seconds on average across 3 prompts. And then its stop time, it was shorter, and then it kind of just like blurted this stuff out, but it wasn't as high as quality. So it wasn't, as far as like the other 4. So we'll see. And it's just known that they're kind of going through their steps right now that I think the other models have been through. Now, the standard deviations for these 3 prompts. So we see at the bottom, this table here, the GPT models being pretty similar with, start, definitely, and then stop. And this was taking, manually on a watch, and then stop being, somewhat similar to. Now, the one that stuck out was this 3.5 Sonnet. It typically ended about the same time. So the standard deviation lower means that it's, more reproducible across the 3 prompts. And also for words too, it typically hovered around this 290 to 300, things like that. So like I said, I think it's an issue. It's not the biggest issue in the world with context window now, but I think it would help a ton, for R&D, especially because I see all these things with RAG workflows, and this is similar to that. It's document retrieval, and they just don't get the results, and you can only do one type of data. I haven't gotten to see that like in a notebook, like just code, that you get this level of performance, but we need that higher context window is the point. Okay. And then, so for words, 3.5 Sonnet, more consistent, lower standard deviation with its number of outputted words. And then Gemini 1.5 Pro, the standard deviations, the time being all over the place. And then it just tends to just like blurt out the answers, in a less quality thing. Okay. So I hope that helps. And again, both of these are up on ChemArchive as manuscripts right now. And then, definitely going to be moving this forward as far as making it more functional, spectra, reactions, definitely drug synthesis type of related types of activities. And I appreciate the continued support. And thanks, everybody. This has been Wednesday, August 28th, 2024 for number 148, LMM Spectrometric IDs of an organic compound. Thanks, everybody, for coming on. Have a good rest of the day and have a productive rest of the week. Take care, everybody. Bye.